Hi everyone, so thanks for the introduction, Mike. Many of you in this room obviously know who I am. I don't believe there's anyone who doesn't know who I am. But yeah, I'm a PhD candidate here in the Learning Sciences, in the Learning Sciences department. And but for those of you who do know me, you may not be familiar with what I've been doing over the past year and a half or so as I've been working on my thesis research. So today I'm going to take us through some preliminary findings from my dissertation work. And over this past year and a half or so, I've been studying how learning environments that leverage embodied actions like gesture can target and improve how students understand spatial concepts in STEM. So I plan today to review some big ideas from embodied theories of learning and show how my research has taken those ideas, distilled some design principles, constructed learning environments, and then posed research questions that I believe will enhance our understanding of this burgeoning area within the learning sciences, namely the study of embodiment. So my work, as you will see throughout today's talk, is situated in the undergraduate organic chemistry classroom, but I am interested in supporting spatial thinking in a broader sense in STEM, and I encourage each and every one of you in the talk here today, as you're listening to me talk about this research, try to see these ideas through your own disciplinary lenses as well, and think about how these principles may apply to the context for which you're also yourself trying to design for. So let's start with some of the big ideas driving this dissertation. First, I want to review in broad strokes a key construct that I'm trying to address in my research, which is spatial thinking. I'm going to return to this idea of spatial thinking at many points today over and over again, so I do want to emphasize up front that spatial thinking is always the learning outcome that I'm trying to target with my learning environment designs. Spatial thinking itself is a big idea, and so I want to address this first before I talk about the ways that I attempt to address and improve it through instruction in my research. So what is spatial thinking? Why does it matter in science, technology, engineering, and mathematics? And how have we tried to teach it? Over a decade ago, the National Research Council convened a panel of spatial cognition and GIS researchers to answer the question, what is spatial thinking and how can we teach it? Through this effort, they provided a framework for identifying both the component skills of spatial thinking and some examples of learning environments that can be used to support its development. For them, spatial thinking is a set of cognitive skills that are integrated tightly into a type of literacy, a new type of literacy that they call spatial literacy. Spatial literacy is a unique way of thinking, and the committee argues that we really should be paying attention to this and seeking to foster it in our students. So if I may, I'm going to draw an analogy here to traditional text-based literacy to give you an idea of what kind of component skills we might be looking for. So at one point in time, the normative understanding of literacy was synonymous with just being able to read and write. Now, however, literacy encompasses a much bigger idea, a much bigger set of expectations. We want students to be able to exhibit fluency with language, images, media, and be able to use those skills to reach a deep understanding of a text. In turn, a literate student should then be able to apply and communicate their understanding through a number of writing and multimedia products. So in a similar way, there are a number of essential characteristics that a spatially literate student should exhibit, and these too are shaped through social norms. They should be able to exhibit a critical knowledge of space, its properties, and be able to exercise that understanding in a critical and informed way. And I think it's important at the beginning of this talk to clarify that spatial thinking is related to, but it is not the same thing as spatial ability. Early psychology was marked with a lot of efforts to devise measures to measure a number of cognitive aptitudes. And so the tests that you see here on this slide all represent attempts to measure different aspects of an individual's spatial ability. Spatial ability really is an umbrella term for a number of component skills like mental rotation and spatial visualization. And each facet of spatial ability has one or more tests that were devised to measure these particular aptitudes. Why do I make this distinction and why is it so important to bring it up front? So I think it's important because a number of studies have argued that how students score on these type of tests correlates with things like their degree and career choice, how much they enjoy STEM coursework, and their performance in some STEM courses. And this has given rise to a model of improving STEM achievement that argues that if we can just simply improve how students score on these type of tests, then they should just excel in science. But I think if we look at these kinds of images, these kind of abstract blocking shapes, it's hard to see how the skills that we're testing with these type of instruments map onto the more complex skills that we want a chemistry student to do in the classroom, an engineering student to do in the classroom, or a mathematics student to do in the classroom. So this is instead why I focus on spatial thinking. Spatial thinking is a broader construct than spatial ability, and the focus on spatial ability, I think is also important to note, has historically tended to propagate a deficit model of understanding in science. So students either have it or they don't, and the students that have it will do well, and the students who don't will fall out of the STEM pipeline. But spatial thinking, on the other hand, reframes the question, and it asks instead, what can students do, what do they know, and what are the things that we need to design for in order to improve their understanding of space, particularly situated within the discipline where it's going to be most useful for them. So this provides us with a framework, both as researchers and designers, to think about how we can design for students to learn about these complex spatial ideas in disciplines. So the National Research Council defines spatial thinking as having three chief components: that students need to have and exercise an understanding of concepts of space, tools of representation, and processes of reasoning. So we'll go down the line. So concepts of space. This refers to the ways that we conceptually divide and define space and why we do so. So take, for example, the ideas of extent, size, dimensionality, symmetry, distance, orthogonality. These are all spatial concepts that are invoked in STEM in various ways to explain complex ideas. And of these three items that define spatial thinking, the knowledge of concepts of space, according to the NRC, is the most important aspect of spatial thinking because it is what makes spatial thinking unique. So we have to support students' understanding of spatial concepts critically in order to get them to be better spatial thinkers. Every STEM discipline also uses extensive tools of representation to depict and operate spatial entities in their respective disciplines. So on our slide here, we can see if I can get my little pointer to work. Okay, we see a 3D manifold surface, a differentiable surface. We see a couple block strata diagrams from geology. We see a series of interlocking gears. These are all representations of inherently spatial things. But don't limit yourself in terms of thinking that this is all that we care about when we talk about tools of representation. Other things like computer visualizations can be used to represent spatial information, agent-based simulations, and GIS maps. All of these things fit under the umbrella of tools of representation. What's worth noting is that representations like these are pervasive in STEM. And we frequently, the further you get into a STEM discipline, the more specialized those representations become, to the point where an outsider may not be able to glean the same amount of information from those representations compared to somebody who's been in the discipline and practicing in the discipline for a period of time. Finally, processes of reasoning. Processes of reasoning really refers to kind of the coordination that we expect of students merging together their understanding of concepts of space and tools of representation to make informed judgments about spatial problems and structure information towards achieving some kind of goal or insight. My work, as I mentioned at the top of the talk, is largely situated in the context of organic chemistry, and the reason is because organic chemistry is a highly spatial discipline. I've picked a few representation or kind of a representative cross sample of the types of things we might ask a student to do, whether it be predicting the outcome of a cyclization reaction, interpret a spectrum by looking at the peaks in an NMR graph, towards doing something even more complex by deducing the structure-function relationship in a large protein structure. These all represent aspects of what we might expect a chemistry student or a biochemistry student to do. And that's why this makes it an ideal discipline in which to investigate the mechanisms by which we can improve spatial thinking. So spatial thinking is important to STEM in a broad sense, but why? So I think the short answer to this question is that spatial thinking has historically served as a driver of discovery and innovation. Here we can see the now photo 51 recorded by Rosalind Franklin using X-ray crystallography that led her to propose that the structure of DNA must be helical in nature. And it wasn't until Franklin was able to capture these X-ray diffraction images that Watson and Crick were able to revise some incorrect assumptions that they had made about the phosphate sugars in the DNA backbone of the DNA molecule. And it was together with these two insights together that we now have a agreed upon model for what DNA and what its structure is. There are really no shortage of examples of how spatial thinking has been central in science, whether that be Dr. John Snow's mapping of morbidity data from 19th century London, tracing a cholera epidemic back to a contaminated well in Soho, and in the process giving us the germ theory of disease, no less. Two more modern examples of, like in 1978, the Citicorp Center was built in Manhattan in the year previous, and it wasn't until an undergraduate had done an independent research project that he discovered this particular design that they had come up with was vulnerable to a type of wind called quartering winds, and this is winds that that hit a building from its corner versus from its face. And this undergrad contacted the architect and said, hey, this building could fall over as it is designed. And it wasn't until they had this insight that they just, they cordoned off that part of Manhattan, reinforced the building, and averted disaster in a sense. But the consequences of spatial thinking are actually quite commonplace, and in pharmacological chemistry, small changes in the structure of a molecule can give way to unforeseen effects. So one example is the drug thalidomide. It was often given to pregnant women in the 1960s, but it was discovered that one isomer of the drug, which means one spatial arrangement of the atoms of the drug, varied only in the orientation of one bond here. You can see I've got it circled. And one isomer of the drug was able to treat nausea, whereas the other isomer of the drug produced fairly profound birth defects. And it wasn't until they discovered this that they found that this was an issue with this particular drug. So spatial thinking is important, and it's consequential in professional STEM settings. This suggests that training students to become effective spatial thinkers is vital if we are to continue producing top-notch scientists. And in fact, spatial thinking is a very common demand that we place on students in the classroom on a day-to-day basis. The problem is, though, in general, spatial thinking isn't targeted directly in the classroom as part of instruction. Rather, we just kind of expect students to pick it up as they go. So if we want to teach students to be better spatial thinkers, this is something we need to turn on its head. And a number of researchers have asked this exact same question: how can we teach students to be better spatial thinkers through both laboratory and classroom interventions? So the training efforts that are out in the literature largely fall into one of two categories, either domain general training or domain specific training. Domain general training refers to training studies that assume that a student's performance in STEM is mediated by their spatial ability. The thinking goes from this line of work that if we can just improve spatial abilities, then students should improve in the classroom. Some examples include studies that have asked students to play Tetris over the course of 12 weeks and then take a mental rotation test each week. The two other studies that you see in the center and on the right, those both use a curriculum devised by Cheryl Sorby, where students are asked to work through a various number of workbook activities that train different spatial topics like drawing orthographic projections, similar to like drawing the blueprint of a room, rotating objects about axes, and then investigating things like reflections and symmetry. However, the authors in these studies, when they do find that there is an increase or an improvement in spatial ability, the connection between that and STEM achievement is not very clear, and in many cases it may not be causal. So some of these studies, either they don't find a connection to STEM performance. If they do find a connection to STEM performance, it tends to be selective, so it doesn't affect all STEM classes. And these benefits do tend to vanish after a period of time, somewhere around 6 months. And in some studies, the benefits that were seen of the spatial training may actually be confounded by the self-selection of the students that took part in the study. The second broad category of learning environments that are used to target spatial thinking are those that use domain-specific tasks. So I've chosen, there are a number of studies, but I've chosen two here. And on the left, we can see an example of a study where a geosciences student was asked to generate some predictive sketches about the internal structure of a geological sample after various cuts had been made. Students have to reason about the internal structure, morphology, and continuity of rock layers in order to accurately make these kinds of predictions. On the right-hand side of the screen, the mouse ever shows up. On the right-hand side of the screen, we see an example from organic chemistry where students are asked to translate between common structural diagrams of organic molecules. Students in this particular study were taught by an instructor how to use representational gestures to both index and transform spatial relationships to generate multiple informationally equivalent structural diagrams. So if we reflect back to the spatial thinking construct, we can see that these interventions are both directly targeting the component skills of that spatial thinking construct. So first, what we see is that both of these interventions are attempting to improve students' understanding of spatial concepts like orthogonal cross-sections in the geosciences example, or transformation in the case of the chemistry example. Second, both interventions are asking the students to engage with discipline and domain-specific representation. So we see these types of diagrams that we would expect a geologist or a chemist to use regularly in their practice. And finally, each student is being guided about the processes of reasoning that are exercised within each discipline. So the geology student is learning how to predict the morphology of the layers inside the rock and create orthogonal slices. This is something that we would expect a field geologist would do as they're trying to wind back the geological clock and make some kind of inference about what happened at some point in the past where they are. The chemistry student similarly is being shown how various structural diagrams can be used to represent the same molecule, and this is something that will become highly important for them as they begin to talk about the energetics of molecules and various reaction mechanisms. What you may or may not have noticed from these two examples is that even though both of these interventions are targeting spatial thinking, they do it using different activity structures. So one is using sketching and predictive sketching, whereas the other is using a set of gestures to represent and transform spatial information. I think it's important to highlight that there is no single approach to improving spatial thinking. Instead, in this particular talk, I want to try and make a case for a particular way of viewing how we could improve spatial thinking. And specifically, I would like to make the case that spatial thinking may be particularly responsive to instruction informed by theories of embodied cognition. I would like to, of course, cover another big idea here, which is the idea of embodied cognition. What do I mean when I use the term embodied, and what relationship does embodiment have to spatial thinking? I will then propose some design principles distilled from this theory that will guide the learning environments I've designed to target spatial thinking in my dissertation. So at its core, embodied cognition represents kind of a sea change in the world of cognitive science that rejects explicitly the classical mind-body dualism. Instead of the body just being a peripheral input system into our cognitive and mental representations, theories of embodied cognition posit that our ability to sense and perceive the world directly shape our cognition. There are competing definitions, even amongst embodiment researchers, though, about what the term embodiment means, and I think it may be illustrative to clear that up first before we get too much further in. So Margaret Wilson, who herself has studied human visual cognition and the links between perception, action, and mental representation, she has provided a summary of 6 different definitions of embodiment and evaluated the evidence supporting each account. And the view of embodiment that she has argued is best supported by evidence is the idea that offline cognition is body-based. This view holds that mental representations that we have about various objects and concepts contain perception and motor traces of our experiences with those ideas that we can then later simulate when a task demands it. So sense impressions like sight, touch, smell, hearing, etc. of our physical world can be recalled even when we are removed in time and space from the act of experiencing those things. So if this idea is new to any of you, I'll just give you kind of a quick example to kind of convince yourself that this is viable. So if I asked you, how do I get from the Learning Sciences Institute to the nearest grocery store? Think about that for a second. Or if I asked you, how do I swing a baseball bat? Chances are that those statements both evoke memories that you have from prior experience of either walking and driving to the nearest grocery store or swinging a bat. You might even see flashes of street signs as you would go on your way to the store, or you might be able to imagine what your muscles feel like at various states of the follow-through of a baseball swing. We are able to do this even though we're not actually engaged in doing either of those things. We're all sitting here in the same room, nobody is playing baseball, but yet we can still recall those with an interesting degree of fidelity to the experience itself. This idea is what's called simulation, and it's at the core of embodiment. The idea that mental representations may automatically reactivate traces of perception and motoric action as we try to make meaning is really quite a different view of cognition than the metaphor of the brain as an information crunching computer. So all that being said, I do want to emphasize that this framing of embodiment should really be seen as a postulate, something that we set out to test explicitly through experimental designs. And in this view of embodiment, and what authors like Lawrence Barcelau call grounded cognition, that's another name you might hear in the literature, there's a proposed feedback loop between what we sense and perceive from the world and the way that mental representations are shaped. I think it's important to draw the distinction between embodiment and embodied actions, because embodiment is ultimately a brain-based phenomenon, whereas embodied actions are the actions that we engage with the world through our sensory faculties. The reason that this is an important distinction to make is because if we ever want to approach a theory of learning derived from embodied cognition that can help us create practical learning environment designs, we can ever only design for what a learner sees or does with their body. It's then up to us to empirically evaluate whether those embodied actions then give rise to embodiment, and then the next step to ask, was that consequential for learning? So one question that I will often get when I talk about this is, well, does that mean that everything is embodied? Does every mental representation contain perception and action traces? I think we're far from a consensus view on this particular point, but Medeyard and colleagues reviewed a number of neuroimaging studies in light of a number of theories of embodiment, and what the authors in this study have proposed is that a weak view of embodiment is currently best supported by experimental evidence. And in this view, mental representations and conception are grounded most often when it evokes mental imagery. So this can involve either visual imagery or motor imagery, and we can most likely say that those phenomena are said to be embodied. So then this brings us to an interesting question. Does spatial thinking have an embodied character? David Waller, a well-known spatial cognition researcher, has proposed that if we are to substantiate the core claims of embodiment, then spatial thought may be the prime context in which we're able to find this evidence. We know from some early work by Stephen Koslin, a spatial cognition and perception researcher, that when people are asked to visualize space and spatial operations, they do make use of analog and imagistic aspects of thought. So I've cited two studies here. The first is when students are asked to make, or when participants are asked to make speeded rotation judgments, so they're looking at images of blocks and they're supposed to mentally imagine rotating them and comparing them. There is a linear relationship between the angular disparity between those blocks and the time it takes them to respond with a match or mismatch answer. This is highly isomorphic to a real-world operation where if we actually had two blocks in front of us, it would take us longer to rotate one that's further separated by an angular disparity than another. And so this indicates that there is some isomorphic mapping between the two. In another study, Koslin and colleagues were asked participants to mentally imagine scanning distances on a map, and the researchers found that the time it took participants to make judgments about varying path lengths on this map were proportional to the actual distances between objects on the map, showing a similar upward linear relationship. So what this suggests is that our processing of space relies on mental representations that have a high degree of isomorphism to the external reference that we are representing. And they appear to be governed by processes of analog manipulation. In addition to visual mental imagery, mental motor imagery may also feature centrally in our understanding of space and spatial relationships. One well-studied example of embodied actions in this sense is the case of gesture. Numerous studies have found that gestures frequently manifest when humans communicate and reason about spatial information. This can be as mundane as giving somebody directions using gesture, to more advanced reasoning about complex ideas in STEM. So here we can see an example of a research scientist discussing how thrombin, which is the enzyme in blood plasma that's responsible for clotting, how thrombin moves as it binds to another protein, thrombomodulin, and you can see she's showing kind of a motion of her hand as she's clamping down. In addition to communicating about space, gestures have also been shown to support spatial cognition on a number of tasks. So specifically, Chu and Kita have demonstrated that gesture can support spatial reasoning on mental visualization tasks. These are classic psychometric tasks. And in a series of experiments, what they show is that when people are encouraged to gesture, they make fewer errors on these classic mental spatial metrics. So taking these findings together from the world of spatial cognition, it suggests that spatial thinking may naturally draw on embodied processes. And so taking that a step further, it suggests that if we wanted to target spatial thinking, then instruction that employs embodied actions may be a reasonable proposal. And indeed, researchers have begun to focus on the role that embodied actions like gesture play in learning. Some of the earliest research on gesture for learning has focused on conceptual understanding of things like number and arithmetic operations in elementary math. But a growing number of studies have looked at the role that gesture plays and can serve in promoting spatial thinking in areas like geometric proofs, statistics, chemistry, and geoscience. I want to highlight these two studies that you see on the slide because in both cases the authors found that embodied actions, here they use gestures, had a positive impact on spatial thinking, but their findings were qualified in a few important ways. And ultimately, since I'm trying to get us to some design principles, I think it's important to identify those caveats in this discussion. The first study on the left that I've already mentioned briefly is a study where students were taught to transform structural diagrams of molecules in organic chemistry using representational gestures to both represent and transform the spatial relationships in each diagram. The outcome of this study was that instruction with gesture was better than just observing gesture or reading a text, and that the benefits were on par with using a concrete model, which is a tool we might expect a student in the organic classroom to have on day one. The authors highlight that it was not enough, though, for the student to just watch somebody else gesturing. They themselves had to perform the gestures in order to pull any benefit from it. Further, the design of this study, and the authors talk about this in their discussion, did not systematically separate what aspects of gesture were supportive of spatial thinking. Was it that the learners were explicitly representing spatial information in gesture, or was it that they were enacting the spatial transformations in gesture, or was it a combination of both? In the study on the right, a group of novice geoscience students were taught how to make interpretations of contour maps containing features like hills, valleys, and slopes. Groups were each given a different type of gesture. One was told to use a tracing gesture to index the various elevations on the contour map, while the other group was given representational gestures that shaped the hand like a number of these features, like a hill, a valley, or a slope. The authors in this study found that both gesture groups outperformed a no instruction, a negative control, so a group of students who didn't get any instruction whatsoever. But it was only the pointing gesture students who had a more effective learning outcome than when compared to an active control, and this was a group of students who were reading a text, which suggests that in this study, pointing gestures were more effective than kind of business as usual, but they didn't have evidence to say that representational gestures were more effective. So while these studies both have positive outcomes, the success was qualified by the observation that, for one, students themselves need to perform the gestures themselves in order to benefit from them. And two, that there may be some trade-off between the types of gestures that we embed in instruction, whether that be to represent spatial information, transform spatial information, or both, that may be responsible for any learning that may occur relative to inappropriate control. So this brings us to our first design principle. So in order for a learning environment to use embodied actions to support spatial thinking, the learning environment should include some kind of explicit scaffold that helps the student map between a spatial entity and what they are going to be doing with their body during the intervention. Scaffolds could include things like having an instructor co-present during learning to provide some guidance and correction while the student is beginning to represent information with their hands, or other perceptual cues that we might embed in a learning environment, like a digital learning environment, that helps them establish the alignment between what they're doing with their body and the spatial concept itself. We also have seen from these studies that the gesture set that was provided to participants had a high fidelity mapping to whatever spatial concept they were asking the student to learn. This is important because embodied action should always be a purposeful movement and intentional. Not all movement is good movement. So in the studies where we've seen that gesture has been beneficial, there was always a clear mapping between the spatial concept itself and the embodied action. This brings us to design principle 2. Embodied learning environments should leverage motoric actions to simulate high fidelity spatial operations that we might otherwise expect the learner to do mentally. So these design principles then I used these to then inform the learning environments that I used in my dissertation. The dissertation is broken down into 2 big studies, and I'm going to be mostly presenting data on study 1 today. And study 1 itself is broken into 2 sub-studies. So for convenience, I'm going to refer to the learning environments themselves, since each learning environment that I'm going to show you today represents one of the sub-studies of study 1. So keep that in mind as we go forward. One outstanding question that I had from the studies that I reviewed is that whenever we know that, so spatial thinking, if we want to improve it via gesture, does the particular form of that gesture matter? So in the study of organic chemistry students, Steiff and colleagues argued that the chemistry students improved at spatial thinking, but that the design did not tease apart the representational features of the gesture versus the enacted features of the gesture, and whether one or the other, or both, was responsible for the learning gains that they observed. In the geoscience student example, Addit et al., their study of the contour maps found evidence that both representational gestures and tracing gestures could produce learning gains compared to no instruction, but it was only the tracing gestures that showed a clear gain over an active control. So in this first study, I designed an experiment to specifically probe this, so whether there was a distinct affordance of either type of gesture for learning the spatial content of organic chemistry that I'm trying to get across. So the questions that drove this work were, to what extent does grounding concepts in embodied actions promote learners' knowledge of spatial concepts? Second, how does the type of gesture differentially impact learning spatial concepts in the domain of organic chemistry? So to answer these questions, I designed a learning environment that aimed to teach naive organic chemistry students about the spatial concepts geometry and symmetry. I designed some video segments where you can see in these images here an instructor uses either a representational gesture or a tracing gesture, or both, to explain how various molecular structures exhibit specific geometry groups or symmetry elements. Consistent with design principle 1, whenever a concept was introduced and whenever students saw a new molecule within the context of these videos, they first always saw a scaffold that explained how the spatial concept could be mapped onto their hand. So we can see an example here where a student is being shown how to trace out the elements of a geometry group. A circle appears on the center atom, and then they're shown to trace their hand by following the motion of the hand on screen, how to trace out the spatial relationships in that particular geometry group. Similar thing also for symmetry. Consistent with design principle 2, as we see over here on the right, the gestures that students saw were all carefully designed so that the motoric action that they were provided mapped out the important spatial relationships relevant to the spatial concepts here that I was trying to teach them. And for those of you who aren't familiar with the content that I'm drawing on, just a very quick baseline on geometry and symmetry. So geometry, you may know this term from mathematics, but for chemists it has a very different meaning. Chemists use this as a way to predict the overall structure of molecules, because we know that in achieving their lowest energy states, electron pairs around atoms and bonds will tend to spread out as far as possible to limit repulsive interactions between those electrons. In the organic classroom, we then ask students to take their understanding of individual atom geometries and chain those together to then predict what the three-dimensional shape of a molecule would be given the individual geometries of the atoms that comprise that molecule. The second concept that I wanted to teach them was symmetry. And symmetry is understood by chemists in a way that's much more similar to how a mathematician would understand it. So there are various symmetry elements that can be used to describe any molecule, like rotational symmetry, planes of reflection, points of inversion. But in this study, I'm exclusively focusing on planes of reflection. So keep in mind, there are more things that fall under the umbrella of symmetry, but I am focusing exclusively on planes of symmetry. And in this particular molecule, this water molecule that I've thrown up here, you can see that there are two planes of symmetry. The red plane of symmetry goes through all of the atoms in the water molecule, and the blue plane of symmetry is oriented orthogonal at a 90-degree angle to that blue plane of symmetry. And why is symmetry important? So we often ask organic students to reason about symmetry in molecules, especially when they're engaged in tasks like inspecting NMR spectra. Many times they need to think about the symmetry elements because when a molecule is symmetric, the signal information that you get out tends to collapse. It reduces the amount of signal information. So students need to reason about whether the molecule is symmetric and if that's giving rise to the reduced amount of signal information that they're seeing. So in this study, to run this study, I recruited students from a second semester general chemistry class. And the reason I chose second semester general chemistry is because this represents the population of students that's then going to go on into the organic chemistry sequence. So participants were recruited, and they were then randomly assigned to be in one of 5 conditions, and you can see I've got the design schematic out here. They were assigned to be in either a self-explanation control group, where they watched a series of videos and took notes about geometry and symmetry. One group of students was assigned a representational gesture that gave them a gesture to represent the spatial information in a symmetry and a geometry element. Another group was given a tracing gesture or an inactive gesture. The fourth condition received both a representational and inactive gesture in sequence. And then the fifth group that you see on the right, that was a passive control. So this control group, they just watched the videos, the same videos that the first control group watched, but they were not asked to take any notes or engage in any self-explanation. Power analysis indicated that we needed at least 25 students per cell. We ended up running 32 students per cell by the end of fall 2017. So that gave us a total of 160 students. The experimental protocol used a pre-test, intervention, post-test design. And prior to the intervention, participants first went through a series of demographic data collection, where I asked them things like their age, their prior chemistry experience, their GPA. They also completed a few psychometric instruments designed to measure their relative baseline of being able to mentally rotate things like block shapes and images of hands. The participants then went on to read a baseline text that introduced them to the spatial concepts, geometry, and symmetry. But you'll notice I didn't use any molecules in this instruction. They just saw these kind of abstract shapes, and they were given just a quick primer on what these concepts meant, without actually giving disciplinary content. So then they then took a timed pretest that assessed 3 subscale measures of spatial thinking. I tested them on their understanding of geometry, symmetry, and also transformation. Each concept subscale had 12 items. On the geometry, when they got to the instruction portion of this study, after they took the pretest, for the geometry part of the segment, they watched a series of 9 videos that introduced the students to a number of molecules exhibiting 4 distinct geometry groups. When they reached the symmetry part of the instruction, they saw 10 videos of varying molecules that varied the number of planes of symmetry that were visible in the molecule, that were contained in the molecule, from either 0 planes of symmetry up to 3 planes of symmetry. All of the videos were kept informationally equivalent, and I systematically varied either whether there was gesture present at all in the video, and then if there was gesture, what type of gesture were the students seeing as part of the instruction. At all stages along this particular study, the students were encouraged to gesture along with the video. I predicted from prior research and a review of the literature that participants in the embodied conditions, which is the representers, the enactors, and the representer enactors, they should outperform both control groups. I also predicted that the representer enactors should gain the most because of the dual reinforcement of the two types of gesture. But I didn't make any specific predictions about whether the representers or the enactors would outperform one another. So to compare whether participants learn more about the targeted spatial concepts as a function of the experimental treatment, I ran a repeated measures ANOVA where I controlled for spatial ability and GPA, and I used both the geometry and symmetry subscales as my repeated measure. The treatment served as the between subjects variable, so the experimental condition. I did assess students on their understanding of transformation in this study, but because I didn't provide any direct instruction on transformation, I didn't run a model on those particular data. So in each bar chart, you can see the mean spatial thinking score for each pretest is shown in blue, and each post-test is shown in green. And then the conditions are laid out here on the bottom, and I apologize, it's a little small. But on the far left here, this is the self-explaining group. These are the representers. These are the enactors. These are the representer enactors. And then this is the passive control group on the far right, which maps onto that previous table that we were looking at. Same thing over here, same layout over here. And below each graph, I've also included just a quick layout of the different components of the repeated measures model that I ran so that you can see what effects I found. So my analysis revealed that in both cases, the student's GPA was statistically correlated with their performance in this particular task, but that variance was partialed out. And when we include that in the model, if we look at the within subjects effects for the geometry students, what I found was that there was a main effect of experimental condition on experimental condition. So what that means is that students gained more in some conditions relative to the others because I saw this statistically significant interaction down here. I then ran a planned contrast after I did this, and you'll notice down here, if this heads-up display thing goes away, you'll notice that condition was not significant. So what I did was I lumped together the control students and I lumped together all of the embodiment students, and I performed a contrast. And what I found was that the students that were in the control conditions, on average, did about 1.3 items better than the embodiment students when we looked at their pre to post test gains. When I looked at symmetry, I didn't find that pre to post test an interaction that I saw in geometry, but instead I saw that there was an interaction with spatial ability. So at this point, what my data suggests is that students in the embodied conditions actually performed worse than when we look at the absolute number of items on the geometry subscale. So it occurred to me, though, it did occur to me, that students who are using the embodied actions may actually be engaged in a more deeply analytical type of thinking that's promoted by the instructions, and they may simply just not have been able to answer as many questions on that post-test. So to investigate that possibility, what I did was I ran a second analysis on the geometry subscale where I calculated first how many questions did they actually answer on the pre-test and post-test, and what percentage of those questions did they get correct, so that we could scale relative to the number of questions that these students were answering. And what I found is when I ran that same repeated measures model, I now no longer saw those differences. So in this particular case, there was no difference by condition. Everybody did better on the post-test, but there was no longer an interaction based on condition. So I have to be honest, I was relieved that there wasn't a negative effect from this particular study, but I was more surprised that the results, they ran contrary to both my predictions and previous literature. So this led me to ask, did students learn anything at all? And was what I'm seeing here from this intervention really just a test-retest effect? And I needed to rule that out. And second, did the time constraint, so I mentioned at a couple points that I was artificially limiting how long students could take to answer these questions. So I wondered, did this time constraint that I was imposing on them actually suppress my ability to detect anything from this intervention because I was artificially limiting the time that they had to look at the questions? So to address these test-retest concerns, What I did was I calculated a discriminability index for all of my spatial thinking test items to see, what was the spread between the students who were in the top 20th percentile and the bottom 20th percentile, and looking for items that allowed me to discriminate those students with high degree of separation. And what I found was that these items actually disproportionately fell into the transformation category. And perhaps this isn't surprising because I didn't teach them this, but I think it's useful for us to use these items going forward if we're going to try and detect whether this intervention does anything by using these items that were more difficult for the students. Also in this graph, what you can see is that I calculated the relative percentage gain from pretest to post-test as a function of the item type, so geometry, symmetry, and transformation. And what you can see is that on transformation items, the students are only improving on average less than 5%, so this suggests that there is a limited test-retest benefit on these particular items. So in following up on this, I decided in study 1.2 to focus specifically on transformation as a concept to see if maybe we might see something different. So this brings us to the question, how do we support students to learn about transformation? So my data from the first learning environment unfortunately suggests that gesturing while watching videos may just not be enough to improve learning over the business as usual type of instruction. So one design that I found in the literature that may have some promise here to helping students perform transformations using embodied actions was recently reported by Stull et al. And in this study, Stull and colleagues, they linked together embodied actions to a responsive computer display where they were teaching naive students how to establish the link between transformations of a molecule and structural diagrams in organic chemistry. Relating diagrams in organic chemistry often requires a student to holistically transform a molecule to be able to see it from different angles. They did this in this particular study by building this contraption that you see here in this photo, where they built a haptic input device, and I don't think you can actually see it, but it's being held behind a monitor that's angled at a 45-degree angle, and on that monitor, they're projecting an image of a virtual molecule. By interacting with this haptic device, though, the student can orient this in any way that they want, and the molecule that they see on the screen will update in kind. The authors in this study found that students were highly accurate at performing the required spatial transformations using this particular design. And one of the particular benefits of making it a virtual molecule is that they had the ability then to constrain what students could do to only task-relevant behaviors. And what they found was this gave them a significant efficiency advantage, and students were quicker at answering these types of questions and picking up the spatial transformations. So this suggests that we may need a third design principle to guide the design of learning environment number 2. So I propose that designs that may be able to enhance learning via embodied actions may need to link those actions to innovative tools like visualizations through interface elements or input devices. And then this brings us to the second learning environment, which is the second half of study 1 of my dissertation. And in learning environment 2, this represents the inclusion of all 3 of the design principles that we've seen, including this new one that I just introduced us to, about linking motoric action to computer visualization and interface elements. And I wanted to understand whether I could use this to target spatial thinking around this spatial concept of transformation. So for this study, I designed a piece of learning technology that allows students to move their body to look at a virtual molecule by assuming multiple perspectives relative to a computer screen. By updating and transforming the student, updating and transforming their perspective, the student is able to see not only an initial and a final state of a transformation, but everything that happens in between, all of those intermediate states that occur between the initial and final state of a transformation. And at the end, I can give a demo of this if people are interested. I embedded this particular interface in a learning environment that represents, like I said, each of the 3 design principles. So first, consistent with design principle number 1, students are provided scaffolds on how spatial entities map to the body. So I wanted students to understand rotation around an axis a spatial axis. And in this image, we can see that the student is being shown how they need to move their body in conjunction with this idea of rotation around a y-axis. Consistent with design principle 2, down here at the bottom, the motions that students engage in are high-fidelity motoric actions that map directly onto this idea of transforming around an axis. The molecule that you see in the display, as I change my perspective from left to right, I'm able to see this molecule as if I were really looking at this thing in front of me from multiple perspectives. And then finally, consistent with design principle 3, this software relies on the use of a webcam to embed the webcam that's embedded in the display of the laptop, and some open source computer vision software to track the location of a student's face relative to what that webcam can see. So this is, webcams are at this point, they're ubiquitous. Nearly every laptop has one built in, and so this allows a student to use this learning environment without having to purchase any specialized hardware. And it's using a unique form of human-computer interaction, specifically enabled by computer vision, to get the student to be engaging in these motoric actions relative to spatial concepts. And for those of you who aren't familiar with this concept and its relation to chemistry, so transformation, this is a general spatial concept, and you may be familiar with it in broad strokes. It refers to the movement of an object around degrees of freedom. And in my particular focus, I want to look at rotation around axes. And so you can see kind of an example of what that looks like here in this video. And in the organic curriculum, we often ask students to imagine viewing a molecule from multiple angles in order to either draw informationally equivalent diagrams, to make judgments about the energetics of a molecule as it transforms, or to be able to predict the certain products of a reaction where they need to look at the molecule from a certain angle to predict orbital overlap preceding the breaking or forming of new bonds. And it's not uncommon to see diagrams like this, like you can see over here on the right, in textbooks, where they quite literally will embed images of eyes into the, oh, I went too far. They will embed images of eyes to establish this idea of we need to be viewing this molecule from different angles. And of course it's to different ends, but in this case it's to show them how to draw the corresponding diagrams below from these two perspectives. All right, so to investigate whether this particular design could help support spatial thinking on transformation, I recruited from the same second semester general chemistry population, again because this is the population of students who go into organic. I am currently in the process of finishing up data collection on this. So I have two versions of the study that I have run. The first version, I kept the time constraint on the pre-test and post-test. And in the second version of the study, I've removed that time constraint, again, trying to get at this idea of whether that's artificially suppressing anything that I might be seeing as a benefit of the instruction. So, and in both cases, so irrespective of the time limit, in both cases, participants were assigned to be in one of three conditions. I have a self-explanation control, just like in the previous study, where they're watching videos and taking notes. I have a embodiment condition. These students are using the software interface that I've designed. And then the third condition was included to be a test-retest condition to also help rule out that this, there isn't a problem with just the way that the instrument is designed itself. And again, I used a pre-test, intervention, post-test design. I collected the same demographic information and IV measures. And I used the same three subscales on the spatial thinking pre-test and post-test. I assessed them on geometry, symmetry, and transformation. But in this study, keep in mind, geometry and symmetry were not instructed. Instead, I was only instructing the students on transformation. I just included them to give us further information about this test-retest issue. The subscales, both had, for geometry and symmetry, had 12 questions, but for the transformation items, I had to add 4 more questions, so it has 16 items. And the reason for this is because as I was designing this, I realized that there were some anatomical limitations to what people can do when they're trying to rotate around certain axes. So initially I had wanted to do rotation around x-axis, y-axis, and z-axis, but the problem is that if you want to get a student to rotate around the z-axis, you're going to be asking them to do kind of weird stuff like this. and that presented some anatomical limitations. Also, for those of you interested in using computer vision, as soon as somebody's face tilts away from the vertical, it loses them entirely. So the software would have been rendered inept. So unfortunately, I had to, I could only test them on x-axis and y-axis, and I instructed them on x-axis and y-axis, but I also included... Sorry?
If they're turned away from the screen.
Yeah, but that also loses their face too.
Yeah, but then they can't see, right?
Well,
so you want them to turn this way, right?
No.
No?
No, they're not rotating. What they're doing is moving around the axis to do a spatially equivalent operation to a transformation. Okay, and I'll do a demo at the end. Excuse me. All right, so I introduced another axis of rotation, which was a vector in the xy plane, because this is something that they could easily do. After they watched a series of videos about rotation around each of these axes, the x-axis, y-axis, and the vector in the xy plane, they then saw side-by-side representations of molecules that, in the control condition, one of those molecules was a video that actually had a molecule animating around the rotational axis. They could play, pause, fast forward, and rewind that video. The students in the embodiment condition were then given the interface to physically move around and enact those transformations around the axis. And then the test-retest condition, I gave these students an article from the New York Times about the LIGO detector detecting some gravitational waves. Okay. In the instruction for the two treatment conditions, I also included some formative assessment prompts where after each molecule that I showed them, I asked them to make judgments about whether it was a match or a mismatch, and then the students would then respond and they would get feedback about whether that was correct or not. And at the end, participants, after they did the post-test, participants took a survey that asked them to assess their understanding of the various spatial concepts before and after the intervention using some Likert type questions. And they were asked to share their solution strategy on transformation items in kind of detail about how they were going about solving these particular items. In this study, I predicted that the embodied students should outperform the control group, and that both of them should outperform the test-retest condition. Now, an analysis of this, best laid plans, what they say. So an analysis of the time version of the study shows that there really was no difference at all within or between subjects. And I think in this, I have both two versions of this. I have on the left, this is the timed version of the study, and informed by study one, I converted this all to a relative proportion so we could see, understanding that some students answer more questions than others, what relative percentage did they get correct. But in the untimed version, students were able to answer every question, so we can actually just look at the absolute number. And what you can see in both cases is that this is remarkably flat. There's really not much change from pre-test to post-test. So again, not what I had predicted, but this is science. And then if we look at the test-retest effects, what I saw here was that, when you give a time constraint, so this is on geometry, when you give a time constraint, it does artificially suppress the number of items that students are able to answer, and when you remove that time constraint, they are able to answer more. And this pre to post gain that we would have seen in the first study, which we might have thought was the learning effect, the test-retest effect, we don't really see much going on here over in the untimed version of the study. But what I do want to point our attention to, and I don't know if this is going to resolve, but if this difference right here becomes something that might be of interest, because this is the embodied action condition, and if I find that the students who are getting this interface all of a sudden are doing better on geometry items, that might indicate that there are some knock-on effects of using this software, even though that wasn't really my intention. I was trying to teach them transformation, but it may be helping them better perceive geometry groups. Okay, and then symmetry, again, remarkably flat, so I looked at both timed and untimed, and there's not much there's no real change between pre and post-test. I also gave them a survey at the end where I asked them to self-assess their understanding. And what I think is interesting, when you ask the students, do you think you did better on transformation, or how do you assess your understanding of transformation, both before and after the intervention? What we see is that so blue is before, red is after. In both the self-explanation control and the embodiment condition, students are shifting from considering themselves average on, if we look kind of at the average of their responses, to being above average, and that's also true for the embodiment, where the responses were centered around average, but we see them moving to the left, where more people were assessing themselves as being above average. So this indicates that students are perceiving themselves as doing better, even if that's not really bearing out in the data itself. And briefly, I know I'm getting kind of short on time, but study 2, this is going to be the next steps of this dissertation. And in study 2, I'm going to perform a process study of the embodied learning environment that we were just looking at in study 1.2. And so I want to try and understand, despite empirical precedent and theory, why I'm failing to replicate the benefits of embodied instruction. And to address this particular question, one idea that occurs to me is that the types of representations may, in fact, themselves matter. So in the studies that have shown a benefit of gesture, specifically the study in chemistry and geoscience, the representations that students are looking at are highly schematic in nature. They contain spatial information, but it's not necessarily explicit unless you have a lot of prior knowledge about those representations. And so in this case, gesture itself may be providing some enhancing benefit for those students to highlight that spatial information that's not necessarily clear in the representations themselves. In my studies, I was using explicitly high fidelity representations, and a student with very little knowledge could come in the door and they could pick up on perceptual cues like shading, size, relative location of the objects in the image, and be able to answer the questions with very little explicit guidance. So it may be that there is actually an interaction between the representations that we use and the benefit of embodied actions for instruction. So I do plan to expand my type of assessment items that I'm going to use in this second study. I'm going to give students both a transformation test that uses these three-dimensional high-fidelity representations, but I also want to introduce the 2D diagrams that we would expect an organic chemistry student to be familiar with. So then if I see a change from pre to post test, what this might indicate is that there may, in fact, like I said, be an interaction between the representation type and embodied actions. And if we see students improving on these types of understanding and interpreting these types of representations, that may indicate that an embodied learning environment like this may serve to get students ready to learn. So that may get them bootstrapped in so that when we throw them in a chemistry textbook, when we throw these slides at them with these line diagrams, these bound line diagrams, they're able to better and more quickly make sense of what they're seeing compared to if they didn't have that instruction. Right. And then just quickly, the process study. Oh, I forgot to fill that out. Okay. And the process study, a couple things that I want to look at. I want to probe student strategies, so I'm going to use a think aloud. And in the post survey that I administered to students in study 2, I got some themes that came back from student responses about how they were solving transformation items. So they were doing things like saying, well, I imagine the whole molecule rotating versus I imagine myself moving around the molecule. Some students were saying, it's like I was seeing the molecule moving in the software while I was solving these problems. Other students talked about whether they could even do the mental visualization at all. Some students said it was just too difficult for them to do. And so they were either adopting piecemeal strategies to just rotate single atoms around an axis versus the entire molecule itself. So I want to get at that by probing them with very pointed questions about what are you doing in the moment to moment, and does that change as a result of the intervention? And another source of this data is, of course, going to be looking at their gesture and language. Do the types of gestures that they use, do those change over time? Do they change as a result of the intervention? Do the things that they choose to represent in their gesture change? Does the frequency of gesture change? Same thing with spatial language. Do they highlight certain things in spatial language before and after the intervention? Does the frequency of that language change as well? All right. And then just as a final slide, in honor of International Women's Day this week, I did want to just acknowledge and pay tribute to some of these brilliant scientists up here on this slide who have all directly shaped my thinking on this project through their own tireless scholarship. Thank you.